Okay, good morning, everyone. After some pause, at least maybe a year or so, if not close to it, we continue this series of SMAC seminars on astrocomputing. And today we are going more really to the scientific side of the seminars. We have, it's my pleasure to introduce Han Uitenbroek, who's visiting the ISC for a while and has been kind to give us a seminar on his super useful tool, RH, radiative transfer code. Javier Trujillo, who's a close collaborator of Han, will introduce him.
Well, okay. Well, Han Uitenbroek is a friend from many years. I think we knew when you were doing your thesis in Utrecht, and I was doing my thesis in Germany, in Freiburg. And then after his thesis with Rob Rutten, you moved as a postdoc to the Harvard Smithsonian Center for Astrophysics. And after several years there, doing very interesting science, he got a position at the Sacramento Peak Observatory. But after our present director, Valentin, became director of the National Solar Observatory, he moved to Boulder. And now he's spending here a sabbatical stay with us and before taking permanent vacations. So one of the important things among many others he has developed during his career is the development of this non-LTE multi-level transfer code, which is publicly available and many people have used it. And today you will have a wonderful opportunity to convince the audience to use it. Okay? So you are very welcome.
Okay. Thank you for the introduction, Javier. It's a pleasure to be here always. And thank you for hosting me for a couple of months. I'm really enjoying that. So I will take you through the basic things of the Rybicky-Hummer RH. It's not radiative transfer by Han, as some people have suggested, but it stands for the Rybicky-Hummer multi-level accelerated lambda iteration method that I've implemented in this code. And that's a method that is used for non-LTE radiative transfer. Now, the code can also do LTE if you want to, but we will get to all the things it can do a little bit later. So I'll give you a slight taste of how this multi-accelerated lambda iteration works and why implementing it is really saving us a lot of time. And then I will take you through the installation. We still have an echo, no? Do you? No. I'll take you through the installation of the code. We can do that. We can try to do that really live online. And then I'll take you through a sample notebook showing you some of the capabilities that I have implemented with a Python package to look at the output files. There's also a set of IDL routines. They may be even easier to use because they have a graphical user interface that I have not duplicated yet in Python. But I think more and more people use Python nowadays rather than IDL. So I'll choose for the IDL, the Python part. So the code, what is RH, is the first LTE, non-LTE radiative transfer code. It's easily configurable. It can deal with multiple species in non-LTE simultaneously using this Mali formalism that was developed by Rybicky-Hummer in the early 90s. The code has 1, 2, 3, and Cartesian versions and a spherical geometric version. All these 4 geometric versions share the basic non-LTE radiative transfer library, basically, that calculates the opacity, that calculates the line profiles, etc. So if you want to compare 1- and 2-dimensional or 3-dimensional results or spherical geometry results, you're guaranteed that in the background they use the same routines and they should be directly comparable. It mostly uses short characteristics in all dimensions, except for the one in the spherical case, where when there are no velocities, then it uses a 4-3A solution. Then I've implemented my partial frequency redistribution for Mali, for multi-level atoms. And that basically is described in the reference paper that I'll mention a little bit later. The code can handle polarization due to the Zeeman effect in atomic and in molecular lines. In some approximations, Hund A and Hund B cases are implemented, and it can calculate the polarization for scattering by Thomson scattering and Rayleigh scattering in the continuum. Also, there are some examples of molecular lines in Non-LTE. At some point, we figured that maybe the CO lines form high enough in the solar atmosphere that non-LTE transitions or non-LTE effects would be important. This is only really when you go off limb, it might be important there. But it is implemented. At the moment, the code only parallelizes over wavelength, and this only works for shared memory machines. There are some Python implementations that distribute load over in much more bigger machines in a 1.5D case, where you treat every column in a big 3D cube one by one, and that can work very well in parallel. There's a Python code written by Ricardo Gaviera that can do it. I have also, if you are interested, I have an example in Python that is even simpler to use to take a 3D cube and calculate the full map in 1.5D approximation, or even in 2D if you want. In 2.5D, actually, yeah. So the code is available from GitHub. You can download it here, and I'll go through the installation a little bit later. The paper describing the PID implementation is basically the reference paper, is the paper from 2001 describing multi-level radiative transfer partial frequency redistribution. Not all the capabilities that the code has are described there, but it's basically the fundamental paper describing the method that I've implemented. If you really want to learn how to run the code, it's best to go to Carlos Quintero's webpage and YouTube channel. He has a wonderful series of lectures there, each about an hour long, going through the different things with example files that are online, he tells me again. So if you're really into trying to install and learn how to use it, I would recommend to go through these lectures. So why do we have to implement such a method as the approximated lambda iteration? Imagine that we have a simple case of coherent scattering, where the emission coefficient is given by some absorption coefficient times the Planck function, plus some scattering coefficient times the angle average mean intensity. And the absorption coefficient is given by the absorption, the alpha plus sigma at the wavelength. Then the source function is simply the ratio of the two, emissivity divided by the absorption. And using those definitions, we can divide it out and define a quantity epsilon. And in this way, write the source function is 1 minus epsilon times the angle average mean intensity J plus epsilon B. For typical conditions in the chromosphere, this epsilon is small. It is of the order 10 to the minus 3, 10 to the minus 4. And as we will see, this causes really the problem of finding a solution. You see that in this case, the source function is actually depending via the mean angle average mean intensity, which is defined in this way as just the angle integration over the line profile of the intensity I. We can write this source function now as an operator working on itself. So this is typically a non-linear equation in the intensity that we have to solve iteratively. Now, the simplest iterative method that we can think of is just take the source function as the solution with the previous estimate. So we have an estimate of the source function. Say we start at the Planck function, and then we calculate the next iteration of our source function just by putting the Planck function here. And this works reasonably well if epsilon is not too small. This is the case for epsilon is 0.1. And you see that we actually still already need about 100 iterations to get close to the actual solution, which is given here in the dashed line. If epsilon gets really small, that even 100 iterations doesn't even get us close. This takes about 10 to the minus 3,000 iterations for epsilon 10 to the minus 3 to get close. And for a one-dimensional solution, this might be feasible. If you're going to do one or two or three-dimensional non-LTE with large model atoms, this is, of course, prohibitively expensive. Now, a very ingenious solution was found to this problem in the sense that you can write this source function equation as a function for one wavelength as a metric equation over depth points. So we could easily solve this equation if the lambda operator were just a multiplication, i.e. if it were a local operator. And in that case, you could just bring this part to the other side and find a solution for S. However, this is not true because radiative transfer tells you that radiation in one location of the atmosphere can come from very different areas, other areas in the atmosphere. And so we have to find a more general solution to that. The genial idea was to split off an approximate part for this lambda. It's called lambda star, and split up this equation for J in the approximate part and some delta J, where delta J is now the difference between the lambda operator operating on the source function, the full lambda operator, minus the approximate lambda operator. And if you now choose the lambda operator, lambda star operator, to be a local operator, then you can find a much better solution next guess by working out this equation. It's just simple algebra to get this solution. Once given that this lambda star is a local operator. And if you implement a method like that, then even the case for epsilon 10 to the minus 4, which is typical for instance, the calcium H and K lines in the chromosphere, can be done in 142 iterations instead of 30,000 iterations or so. So this method is very efficient. And this is the general idea that is implemented in the RH multi-level code. To even improve on that, the code also implements what is called NG acceleration, where you can use NG acceleration is a method that is not aware of the physics, but it's really a mathematical trick that if you have a series of solutions that obey the same physical principles, then you can find an optimal extrapolation for your next guess. And this is what the method implements. I won't go over exactly the details, but if you implement that method, then you can do the same problem for epsilon 10 to the minus 4 in only 27 iterations. So this is really a very efficient numerical saver. The one thing that you have to be careful using this NG acceleration, if you have more complicated situations with model atoms that have lines at very different levels at a very different wavelength, since this method is not aware of the physics, it may, if you turn it on too early in the iteration process, it may lead to negative population numbers, which then makes the code diverge. So you have to be, but there are parameters that you can set in the input file that allow you to tune this for different situations. there any questions on this? Okay, so how to install and what do we need for installing it? You basically only need make, a C compiler, and a G-Fortran compiler. Then you can just download the code by git clone from this address. You go to the main directory where you downloaded the files, the RH directory. You type make, and then in each of the 4 subdirectories for the different geometries, you type make again. And then to run the code, the main code, you use you can go to a run directory, which is typically a subdirectory of the geometric directory, RHF1D in this case, for the one-dimensional case. You run the code by $/RHF1D, and then I'll get back to that a little bit later, but in general, the direction that you're interested in for calculating the intensity is not part of the angular grid that is chosen to optimize the integration of the radiative rates. So you can do a separate solution for that direction, where the code uses then the population numbers and the mean angle average mean intensities that was generated in this first solution to solve the non-LTE problem in any given direction. The directory structure of the code is as follows. After you download it, in the typically now it's called RH directory. I used to call it version 2 because in version 1 I only had 1 active atom, so I could only solve for 1 atom in non-LTE. But version 2 added the possibility of solving multiple atoms in non-LTE. So this code, when you build make, it builds the 2 libraries, the general library with all the routines that needed, and then a library with 2 Fortran routines that were more easily programmed in Fortran because they use complex numbers, which C doesn't have a natural class for. Then there are routines, IDL and Python, 2 directories. There's an atlas that comes with the package from the GitHub that has a solar intensity atlas at this center. And there are some tools, for instance, tools to make an arbitrary large hydrogen model atom, and tools to calculate some approximations for collisions if you can't find them in databases. There's a routine to transform Kourous type atmospheres to RH input file, RH style input files. Then there are the 4 geometry directories. And in each of the 3 plane parallel plane cases, there is the executable of the program itself, and then the solve ray to calculate the intensity in any given direction. And then typically you would create different run directories for different cases in each of these as subdirectories. If you keep that general structure, then it's very easy to use, I think, the code. I'll go through some of the input files. The main input file is called keyword.input. It sets a number of parameters, but it also sets the files that contain the atoms. It's a list of atom.atom files. I'll show you an example a little bit later. There's a list of molecular files, and each of those can possibly have a list of molecular lines. The molecular equilibrium, I'll give an example a little bit later, is actually set by which molecules you include here. So if you only want to calculate H2, which is actually required, and CO, then you just put those 2 molecules and the chemical equilibrium solution automatically adjusts to that situation. Then you have an input atmosphere, a magnetic field structure, abundances, and you can include a list of lines that are treated in LTE, regardless of whether you have non-LTE files in your atoms.input. But you can also add a list of lines in the Kourous format exactly how you download them from the Crucis website. So these are the main input files. The Atmos files, of course, in the different geometric cases, specifies the dimensions, the boundary conditions. For instance, in 3D, you have periodic boundary conditions on the horizontal directions. And you have a thermalized boundary condition at the bottom and a zero radiation at the top. But you can also set different values. There's then the temperature. The code requires electron density, although there is a routine to calculate electron density if it's not provided in the .atmos file. There's hydrogen density, microturbulence, and velocity, which depends, of course, on the geometry. In the one-dimensional case, there's only vertical velocity. In the other geometries, there's also the different horizontal velocities. Then there's a separate input file. This for the magnetic field. This has a little bit of historic reasons. When I developed the code, multi was by Mats Carlson was the code that everyone used it. And I wanted to be compatible with that. So I didn't want to change my one-dimensional .atmos file, which is exactly the same as is the case in multi. So I added a separate file for the magnetic field, and this specifies the field strength, the field inclination, the field azimuth. Then each of these atom files have an ID, calcium, for instance. Then you specify the energy levels, the list of bound-bound transitions, the list of bound-free transitions, and the collisions. And for each of these quantities, there are different quantities that are needed. For instance, the energy level needs a statistical weight, a level label, ionization state specification, and of course the energy itself. For the bound list, you need which levels specific lines are connecting, the oscillator strength, the line shape, whether you want to treat the line in PRD or CRD. Then some parameters that are used to determine the wavelength grid for each line. I'll come back to that a little bit later, but in non-LTE, you read a good estimate for the radiative rates. And for that, you need to evaluate the rate over the whole line profile. And instead of leaving it up to the user, the code determines the wavelength grid with a dense grid in the core of the line and a sparser grid in the line wings, so that at least the radiative rates are properly represented. And then there's the different broadening parameters. And similar ideas or things are needed for the bound-free, the ionization transitions, and the collisional transitions. So let me give you an example of what's in this keyword.input file. It specifies, first of all, the atmospheric input file, then a file with abundances for 100 elements or so. Then in the one-dimensional case, the number of rays. These are used to calculate, again, the radiative rates properly by integrating over a solid angle. And so therefore, they need to be chosen carefully. In this case, they are the 0 points of the Gauss-Legendre polynomials. Then there's the atoms.input file, molecules.input file. If you want to calculate either molecular lines or Kourous line list, then you have to specify all the wave lengths that cover those lines, because they're not automatically generated from the .atom files. Then the code does a couple of lambda iterations to get the background scattering. In the solar atmosphere, this is very mild because the opacities, because of Thomson scattering by electrons and Rayleigh scattering by helium and hydrogen, are relatively small compared to the typical line opacities. Then you can set the maximum number of iterations so that the code doesn't endlessly start to try to find a solution if it doesn't converge. You can typically set this to 10⁻², the iteration limit, This is the minimum amount of delta population number that you require to call a solution converged. Then these are some parameters that you can set for this NG acceleration. You can set the order, how many every iterations you want to do, and how many iterations you have to wait before you turn on the process. Then there are some parameters for PID. Won't go into that here, it's a bit too much. There are some file names that you can specify. You can generally change all the opacity, the metallicities if you want, so that all the background opacities basically are reduced or enhanced by the same factor. Then this is the file that has the list of Courous lines. This file, Courous.input, it always needs to be there. It contains the partition functions for all the elements from neutral to something like the fourth or so or fifth ionization state, so that in case of LTE, the proper opacities can be calculated. You can choose to set hydrogen population numbers in LTE in the background. Then they are just calculated from the temperature, given the hydrogen number densities. You can do solutions for hydrostatic equilibrium if you wish to. Yeah, there's some names. There are some other input parameters that are more technical in detail that I won't talk about. And then there are some parameters that if you specify a magnetic field, then you can choose different options for the polarized radiative transfer. And you can turn on or off the background polarization. And you can set the number of threads that is used for the parallel solution in wavelengths. Then, to show you a typical atoms.input file, this particular file has only 4 atoms that will be then treated. If you set it to active, then the multi-level accelerated lambda is applied to this atom. If you set it to passive, either you can set it to LTE population or 0 radiation, which is then the initial solution. Or if you specify a population file, you can read in, for instance, the population numbers from a previous run, provided, of course, that you use the same input atmosphere. Then this is a typical molecular input file. Again, the chemical equilibrium is calculated on the basis of which molecules you include. These molecule files at the top have a specification of the molecule. So H2 is then interpreted as a diatomic molecule consisting of 2 hydrogen atoms, etc. Same for more complicated molecules. And the code then figures out how to set up the chemical equilibrium equations that are then solved with a Newton-Raphson approximate or iteration scheme. So again, a little bit, one word more about this, the wavelength choice, that to represent a bound or a bound-free transition that are used to calculate population numbers, we need to solve statistical equilibrium, which is the equilibrium that finds the solution for a given set of collisional and radiative rates. And to properly represent the radiative rates, you need to have a good wavelength distribution where the wavelength grid is dense in the core of the line, so that the line shape which varies most with wavelength in the line core is represented properly, and the wavelength grid can be more sparse in the wings of the lines. So if you have this set of transitions in your model atom, for instance, and this particular case, these are the 2 magnesium 2 H and K lines, then all of these lines generate a set of wavelengths that are then ordered and sorted in increasing wavelength, and that are then used in the formal solution of the equation of radiative transfer. So I won't have examples, but there is a graphical user interface that you can use. How to run it and start it is described probably in your lectures as well. It is briefly described in the manual that is by now very, very old. So I would recommend to go to Carlos's page instead and learn how to do it. But there is a graphical user interface that can be used to read all the output file that the code generates and make plots with pointing and clicking. It's very easy to use. Then if you want to use the Python routines, they don't depend on much. They depend on one library that is, since Python 13, no longer part of the standard distribution. So you have to install it with this from this distribution. This is used to read files in the XDR format in IDL. This is very easy because you just, when you open a file, you just say /XDR and it reads this XDR. So XDR is a architecture independent way of writing files. When I started developing the code, we had a mixture of little endian and big endian machines at NSO, and I wanted to be not sensitive to that, being able to read files that are generated on one with the other. And so all the output files are written in binary with the XDR lib. In Python, it's a little bit more tricky to read them, but it's not. Once you learn how to do it, you can just cut and paste the routines. So I think that is my presentation here. So let's go to the notebook. Oh no, we're going to install the code, right? So let me go. Oh, let me see this. Yeah. Okay, let me take a clean window. So let me take. Can you read this? So let me make a scratch directory so that it don't mess anything up. And then let me download the code. I'm a slow typer, sorry. So this should do it. So this, oh, it's really slow. Not sure why. Oh, there you go. It hurt me. Okay, so it downloaded the RH directory. So if we go into this RH directory, we see all the common routines. We see the RH here, RHF1D, the one-dimensional, the RHSC2D, the two-dimensional, the three-dimensional, and the spherical versions in different directories. There's the directory with molecules. There's the directory with atmospheres, atoms. There are some docs. There's the very simple manual that you shouldn't read anymore. There's the Python routines, the IDL routines should be here. Yes, here. And there's the directory with tools. So the only thing we have to do here, if you have a C compiler and Gfortran installed, is make, and it will quickly build the routine, the two libraries. And then we go into RHF1D directory and make. Again, it compiles the geometry specific files, links them to the two libraries, and builds the executables. So we have RHF1D and solved, and solve-ray. Solve1D is a different one. There's also a routine that allows you to write the individual background opacity contributions to a file that you then can read. But that's not documented anywhere. So if we go to the run directory, we should be able to run the code. So there we did a polarized radiative transfer solution of the calcium HNK with partial frequency redistribution. And now we also, sorry for those online, that must have sounded off. So now we calculated all the intensities also for the vertical direction. And this created the file spectrum-1.00, which is 1.00 is the mu value, cosine of the viewing angle. So all these files now, the .out and the .dat files can be read with the IDL and Python routines. So let me go to that. So there is, I will upload this to the, I haven't yet, but there is, not here, it's not, it's of course in my regular distribution. Oh, I need to be in a window where I have the. Okay. So I can start it. Hopefully. Yeah. Okay. So we only need a few. In this example, I think OS is not even needed, but we definitely need NumPy and some plotting, the plotting routines, packages. Then you have to put the Python RH analyze directory in your Python path if you want to do this. Otherwise, it won't see these routines. Then there are some tools in the rhtools.py file that we import it this way. And then to use the atlas, you use this. So now I have two directories that I already created with, how are we doing in time? So I can, let me just to show you how to do that, for instance. No. So I have, so by default, there is the code comes already with a run directory that has the example that we just run after I downloaded the code. So what you would typically do if you wanted to calculate a different situation, you would do this. You would make a directory, like for instance, example, go into that directory. It's empty, so copy the input files, input to dot, So now we have the input files. Then we can edit the, for instance, keyword.input file. For instance, if I want to take a different model atmosphere, I can do this. And then if I want to, oops. If I want to then edit the atoms file, for instance, if I also want to add non-LTE iterations of hydrogen in this case, because I only had calcium 2 in this case, and I want to add as well sodium. This. Then I can now run with a different set of input. Oh, and I forgot one. Oh, I can better do this. So it needs the magnetic field, but in this case, let's just turn off the magnetic field. So we don't want Stokes, we don't want polarized radiative transfer. So we just comment out the magnetic field and a different. And now it should run. So now it did a non-LTE solution of hydrogen, calcium, and sodium, and calculated all the line profiles. So I did something similar for these examples. So just to read the different, oops, and there you go. I didn't run it from the start. So you just specify the different output directories like we just did in the example, and you create different structures for each of the different runs. Then, for instance, so I did a run with the same setup. I changed the model atmosphere, and in this case I used the val C and the val F, and these are their different temperature structures. So val F is basically the same temperature throughout the photosphere, a little bit hotter, and then it's hotter in the chromosphere and the transition region. Now, if you calculate the, then if you plot here now locked, so let me just show you what I do here. So this output structure that is created when you read in the output directory has different objects in it, and one of them is geometry, and then in geometry you have the column mass. And in geometry, you also have the optical depth at 500 nanometers. And in Atmos, you have the ID. So it uses those objects to then read the input and output data and create this plot. So you see that I plotted here, for instance, the optical depth at 500 nanometer against the column mass. And you see that they are very almost identical deep in the photosphere. But then in the chromosphere, the optical depth at 500 nanometer is a little bit higher in the hotter model. And that is because there's more H minus when there are more free electrons. And that's why the opacity at 500 nanometer is basically higher. Then you can read in the atlas. So let's do that. And you can, so the atom structure in RH out.atoms, so the output structure .atoms, has a list of all the atoms that were calculated in non-LTE. And for instance, atom 0, if you see, which you can print this first line here prints the IDs for the different atoms. So we have calcium, hydrogen, and sodium. This is easy to, they're not necessarily will appear in the same order as they are in your atoms.input file. So this is an easy way to figure that out. Then you can say, well, calcium is the first atom in that list. And in calcium, I can print for instance, the energy levels, calcium2.e, or I can print all the wavelengths of all the line transitions. So calcium2.transition from 0 to calcium2.n line, the number of lines in the model. And here are the wavelengths, calcium, H and K, K and H, the 3 infrared triplet lines. And you can do similar things for the continuum transitions. Then if you wanted to plot the intensity for the different mu angles, you see that I have here the different mu angles that are the 0 points of the Gauss-Legendre in angular distribution. And I also read in the center intensity here in blue. And the way I plot that is here. It's RH out, raise 0, which reads the files that are generated by the solve rate, .I, intensity. And for each of the mu angles, it plots the spectrum .I for the different mu values and all the wavelengths. I'm going, keep doing that. I'm going pretty fast, but I will make this notebook. I'll upload it to the GitHub so that if you're interested, you can go through it yourself. Then if you wanted to compare, for instance, the intensity at this center for the Val C with the atlas in absolute intensity, this is the plot. You see that in the core of the line, it's pretty good. There's definitely some missing opacity in the continuum for this shorter wavelength. And then if we wanted to compare the intensities for the different model atmospheres with the atlas, then you see that because the temperature in the photosphere and the chromosphere in the two atmospheric models were very similar, the line intensities only vary in the core of the line, which forms in the chromosphere in the higher layers. And definitely the emission in the Val F model is much more pronounced than in blue here in the Val C model. And we can do the same for the wavelength. So basically I'm using I'm printing the wavelengths for all the sodium lines. Then I choose the first two and I take the average of the central wavelength of the true sodium D lines to just make that the central point of my plot. And then this is the comparison between the atlas and the sodium D lines. And you see that it's hard to see, but in the core of the sodium D line, the orange line is slightly higher, while the blue line is actually following the atlas almost perfectly.
Here in the continuum, or for smaller than for plasma K, is it good?
Well, either the temperature of the FALMO is not exactly as it should be, or my opacities miss some opacity contribution. I don't know. And this is an absolute intensity comparison. So this is actually pretty amazing that it's so close. Yeah, sure, that too. One of the next panels will be that exactly. Yeah. No, this is what do you mean, Kurus opacities? So I have my own opacity package that uses, H minus, bound free opacities, and I'm not sure what it would be, but you cannot disambiguate between the temperature not being exactly right, or it's a one-dimensional model, so the temperature, you cannot expect the temperature to be right at all wavelengths, for all wavelengths. If I make the same plot of the calcium infrared triplet, the atlas and the calculated profiles are dead on. So they are all identical. So here we can plot, for instance, the 4 Stokes parameters. So here is the 8542 compared to the atlas. You see, it's almost perfect, which is scary if you once you realize all the calculations that are going into that to make that happen. It's pretty amazing. It's one of my most satisfying plots, I should say. And then there's the Q, U, and V Stokes profiles for, I think this was a 1500 Gauss magnetic field, or maybe 500 at a 45-degree angle, so that I also have Q and U. Then a little word about molecules. In this case, I had included 12 molecules. These are their IDs. Then we can plot the different molecular densities. For instance, H2CO. So we can find H2 is the first molecule. That's why I use 0 here. CO is the 7th, which then I use index 6. And I also plot the H- number density, which is here in dashed line as a function of tau 500 in the file C. And you see that H2 is actually the most abundant molecules, but H2 doesn't have any strong lines. CO has many more prominent lines, and the number density is almost the same as in H2. These are all the 12 then plotted as a function of tau 500. And here is I should run this, I guess. So here is now the flux of the two models. So RH out spectrum.flux has the flux for all wavelengths. And you see that they're only different here, mostly at the maximum of the intensity or the flux, because this actually is also where the H- opacity is maximum, and so this forms higher in the atmosphere. So the hotter model has slightly a larger flux at these wavelengths. Then there's a tool, if you wanted, for instance, to calculate the G-band intensities, you have to create a wavelength grid because these are LTE lines. So in this case, it generates a wavelength grid between 429 and 332 nanometers, 3000 wavelengths in total. And it writes it to a file that you then can refer to in the keyword.input file. And so I did the calculation just before here. I took only the H2, CH, and CO and CN molecules. Actually, CH number density depends significantly, especially in cooler models, on the CO number density. So you cannot just calculate isolate the CH number density. And then I read in the atlas at around 430 nanometers and plot here the spectrum as calculated from the CH molecular line list. And so you see that it actually matches very well, except there's some, again, missing opacities. The further to the blue, that's more and more of a problem. So I think that's what I wanted to show.
Thanks a lot. Really beautiful and impressive.
I hope you have some sense of what you could do with the
Yes,
code.
thanks so much. Well, I must say that one looks at the organization of the code is really amazing. All clean, well organized, versatile. It is.
Thanks. Yeah.
Excellent.
And I only showed examples from the one dimensional case, but you can do exactly the same kind of things with the other geometries.
Well, it's really something we should look into. Do you also go into the 3D and so for some other day we should organize another one. Do you have some time for questions? Comments?
We should have
Yeah, we can repeat the question.
So, of course, I know the code for many years, and it's something they're confident about how well it is organized. But I have a question. So, for example, if one wants to add something, some integrated or radical, to run the code with number densities that come from a different code,
Yeah.
or with capacities that
Yes.
with code, or just to say the number densities or the capacities in a form of, for example, for a table, for a range, temperature, and suppression. How difficult it would be to do it in RH? And do you have a wish to the users can add things and then point happen in code?
We should maybe repeat the question because they didn't.
Yeah. So one thing is if the code would allow you to import and export number densities, I'm assuming from different atoms or molecules even. If you...
The chemistry, including the...
Yeah, so yes. There is already for molecular density. So if you wanted to do non-equilibrium chemistry for CO, for instance, which Javier has worked on a long time ago with Andres, then there is a facility to import those number densities and calculate the lines with those number densities. That's already there. The number densities are by default all written out, so you can use exactly the Python routines that I'm using here to read those files and export the number densities, either molecular or number or calculated non-LTE atomic densities.
What about your capacitance? I mean, can you generate a script of your capacitance?
Yes. Yeah, so that could be done. You could use the two. Remember, we did that with your student. Yeah, Andrea. Yeah. So you could make a grid of different temperature or matrix of different temperatures and densities, and calculate the opacities, and then there's ways to read those. That's also written to a file that's output, and then it's a little bit more intricate to read because I try to save space. Imagine that you have velocities and then wavelengths that have a line included, have opacities that vary with angle, while opacities that are just like H minus that don't have that, they only they have the same opacity for all angles. So the code tries to optimize the space it uses by looking for that. So it's a little bit more intricate to read them, but if you only have continuum opacities, maybe with velocity set to 0, then it would be easy to read as a function of wavelength. So yeah, that would not be hard to. It would take a little bit of attention, but it's not a default option. But that's not hard to do.
Any further questions? Maybe come here.
But having said that, what are the present limitations of the code?
The present
Where do you think there is a room for improvement?
Well, definitely in the 2- and 3-dimensional case, that there should be a better way of parallelizing.
So right now, with the 3D version of the code, it will not be feasible to do calculation for a fiber-level atom, HNK lines of calcium and radiative in a bipolar model or another model.
Yeah, but it would have to be a smaller cube. Yeah, but I've done. It's not impossible. But, yeah, that's definitely one thing. I think I would do it differently than other codes. I think I have some ideas, but I just need like 4 weeks of dedicated time, with no one bothering me, and then I can do it.
Certainly the code includes polarization due to the
Zeeman effect, yes. Yes.
And are you using for calculation the critical emission? So
yes. Yeah.
Assuming that there is no
that is an option. You can also calculate the radiative rates with the full splitting already there. Yeah, then it becomes a little bit slower. Yeah. For 1D, it's actually not a yeah.
Jason, could you come over here to formulate the questions if it's possible? So I think it's very tempting for me to lock you in the room for 4 weeks.
Thank you very much for the code and presenting it. And I just have a question regarding the feedback on the structure of the atmosphere. Do you have that included in there?
No. So this is just a code that does forward modeling. The only thing it can, so you can, there's 2 things that the code can change in the atmosphere, and that's only in the there's one option in the one-dimensional case where you can calculate hydrostatic equilibrium. So then it would adjust the structure of the atmosphere so that it is in hydrostatic equilibrium. And in all versions, you can calculate the electron density in LTE. Well, actually also non-LTE. It actually uses charge conservation. So if you have a solution that has hydrogen in non-LTE and you read it in, then the electron density in the chromosphere is calculated from charge balance. So it calculates how many electrons you have depending on how many protons you have.
So it will change also the background capacity that you will have.
Yeah, so if you would have, it would be a 2-step then, because you would have to solve, or you have to iterate. But I mostly use the possibility of calculating electron densities when I do non-LTE, when, for instance, the rest of the structure doesn't change, but the model atmosphere that you have coming from a simulation or so doesn't necessarily provide the electron densities.
Yeah.
And then they can be calculated by the code itself.
Any further comments or questions? No. Well, I think we can stop here. Han will be here until the end of November.
End of November, yes, for another month.
So he's sharing office with me. So welcome to
yeah. If you are interested.
Before we lock him.
I will upload the Python notebook to the GitHub so that it's part, and you can have a look if you're interested in how to.
Maybe you already mentioned that, but under what kind of license your code is operating?
I have none. I just I think in the end, so I debated, of course, when I started the code, whether I would keep it for myself or give it only out to people that I work with, or make it generally available. And in the end, I think it is really very satisfying to have made it publicly available, because so many people have been able to fortunately use it. I think on Google Scholar, the number of citations for the 2001 paper is over 500 now. So many people have used, even outside solar physics, some but yeah, I do rely on people's goodwill and not misuse it. It's not under any license. Maybe I should think about that.
Okay, we thank you for doing that. Okay, just to mention quickly that we have another SMAC talk line for next week. We go from the atmosphere to the interiors. It will be about the MESA library for computing models of stellar structure and evolution. Okay. It will be Desmond Grossman and Paul Beck. Thanks, Femo.
Yeah.